So now it's time for us to get into the next very large portion of this course. In some ways, perhaps the most significant part of the first semester of first year physics is dynamics, and specifically dealing with forces. And so let's start by defining what the word dynamics means and how it's different than what we've talked about up until this point, which was kinematics. Well, dynamics adds a little bit more, maybe a lot more, to the idea of motion, because it is the relationship between motion and the forces that cause it. Or stop it. That would be equally valid. And this is very, very different than kinematics, where in kinematics, we did just focus specifically on what the motion was once it gets started. And so if you recall, we never talked about what it means to kick a soccer ball or to throw a ball or to, what forces are involved in accelerating the car, for example. All we talked about was the motion of an object once we knew kind of like its initial conditions and what was happening after that. Now we want to talk about what is causing motion to occur and what is stopping motion from occurring. And the answer to both of those is forces. And so really, even though we call this dynamics, in many ways this is a whole few chapters about forces. And we'll have a number of videos on this, lots of examples. And so if we're going to talk about forces, I think it's important for us to start thinking about what is a force. And so we are very familiar with the word force, whether we've taken high school physics or not. And we certainly, in our own heads, have a catalog of forces that we can access. And so what I'd like everyone to do at this point is to maybe write down some of the forces that they can name off the top of their head. Feel free to pause the video as you do. The common forces that I usually hear in a classroom when I ask this question are gravity. We hear that a lot, for sure. Magnetism, I get that one quite a lot. Sometimes, though not often, people will say electricity or electromagnetism. Friction, that one is very famous. Everyone seems to get the frictional force since it plays a very important part of our lives. But what about more like simple things? What about like a pushing force or a pulling force? Or other types of resistive forces like friction. So friction is kind of a resistive force between surfaces, but if something's moving through the air, there's often resistance as well, or through water. And so let's also write with friction, we'll put air resistance. Throw that down here. Let's see, anything else? Spring. Spring force or elastic force often comes up as well. And sometimes people rarely will talk about tension as well. Though in many ways that is related to that one there. And so these are fine, and maybe you've come up with a few additional forces yourself. But when we're talking about forces, it's important for us to think about sort of the fundamental forces of the universe. What forces in our universe do we know exist, and which are actually just variations of these forces? Oh, there's one more that people often give me. If you've taken high school physics, you'll have heard of the normal force. For those that haven't, we will talk about the normal force at some point very, very soon. But going back, let's talk about the 4 fundamental forces of nature. And physicists have found that these 4 fundamental forces of nature are the ones that dictate much of what happens in dynamics on a particle level, on an atomic level, on a macro level that we are very conscious of. And the ones that come to mind right away are the first 2, that is the gravitational force. And so that will be a very, very important force that we deal with in this class. It's a fundamental force as well as a force that affects the dynamics of our everyday lives in so many ways. The next one is the electromagnetic force. The electromagnetic force, again, is very, very important. Let's say a gravitational, electromagnetism. Electromagnetic is nice. And so conventionally we think of electricity and magnetism as 2 things, but physicists have shown that they're in fact 2 parts of the same force. And that force is going to play a very important role in sort of next semester's physics. And the second half of first year physics is so much about electromagnetism. There's 2 types of other forces that are far less famous, and they are called the strong nuclear force and the weak nuclear force. And we won't get into these in first year physics. These are the types of forces that play an important role inside atoms and inside particles. And so you're saying to yourself, well, looking at this list, it seems very, very incomplete compared to the list that we had made previously. But many of these forces, these common everyday names for forces, are variations on the forces that we have defined as fundamental. Gravity and magnetism and electricity pop up just as we see, but all of these like contact forces, these so-called pushing and pulling and tension, etc., friction, these sorts of forces are a form of the electromagnetic force. We'll see over time that when 2 surfaces contact one another, there is actually no contact on an atomic level. That in fact, when you touch your fingers together like this, that you're not actually touching anything. That is, the atoms from this finger are not touching the atoms from that finger. What you're feeling is a resistive force that is pushing against one another, basically repelling each other. But that's a story for another day. One thing that I'd actually like you to start to think about with regard to forces is the mechanism by which force is transferred from one thing to another. And this sort of property of force is something that I'm not going to answer, but I want you to start to consider. So we'll talk about some of the properties of forces. And the first one is, what is the agent of force? That sounds awesome. The agent of force. What I mean by that is, what is kind of our mechanism by which force gets transferred? Is it a contact force? Are 2 things touching in a conventional sense, not in the electromagnetic sense? Or is it force at a distance? How does that work? How do you get force at a distance? And what we mean by that is simply the sun is responsible for the Earth orbiting it, but we're not touching the sun. The sun is creating a force at some distance. So I want us to start thinking about how things can affect one another from far away, or close up, and maybe even start to ponder questions like, if the sun were to suddenly disappear, but it's not going to happen, but let's pretend for a second that the sun suddenly disappeared, would the Earth know right away? Would the Earth, well, what would fundamentally happen is the Earth would end up being shot out in a straight line, similar to if you had a rock on a string, you were twirling it around, and suddenly the string breaks, the rock's going to shoot out in a straight line. The Earth would do the same thing, but the question is, how long until the Earth realized that the sun was gone? Would it be right away? Would it take some amount of time? It's an interesting question that I encourage you to start to think about as we go forward. But other properties of forces come from our Newton's laws of motion. And so we're back to thinking about why motion happens. And so this is one thing that is sort of fundamentally produced by Isaac Newton. I mean, there were scientists that were around before Isaac Newton, but many of those scientists were not in the game of trying to answer how and why, but just what. Like modeling the motion of objects. Galileo, and certainly centuries before him, people were more interested in trying to figure out what was happening. And once we get to Isaac Newton, we start to ponder more things about how is something happening or why is something happening. And it allows Isaac Newton to start getting into some fundamental theories that explain motion, not just on Earth, but across the universe. And his laws of motion, and these are our laws of dynamics, not kinematics, can be summarized in sort of 3 rules. Let's start with the first one, and it says, a body remains in a state of rest or in uniform motion unless acted upon by an outside force. All right, let me think about that. A body remains in a state of rest or in uniform motion unless acted upon by an outside force. Okay, I understand what rest means, not moving. Uniform motion means to have a constant velocity, continue in the same direction with the same speed. That doesn't seem to really correspond to what I understand here on Earth. I think we need to do a quick little experiment. Okay, hey, welcome back. Here we are in lovely Paris, France, here to demonstrate Newton's first law, that is an object at rest remains at rest and an object in motion remains in motion. So let's do an experiment and see what happens. And so I brought my chair out here as well, and let's try the first part first. Here we go. Okay. The chair is at rest. Let's see if it stays there. Yeah, it totally does. And so it's interesting because I would have thought there was a force on this chair, yet it continues to remain at rest. What's going on here? Certainly there's a force of gravity on this chair downwards, but there must also be another force on it that's equal and opposite to that gravitational force that's balancing it out, giving a net force of 0. That's exactly what's happening. We'll learn about that force later. It's called the normal force. Let's try the other part of our experiment now, where we're going to give a velocity, a uniform motion to our chair, and we're going to see what happens to it. Okay, let's make sure we're not getting in these people's photo. All right, or I'll start over here, and I will, once the chair leaves my hand, it will be traveling with uniform motion. Let's see what that looks like. And so it didn't. The chair came to a stop fairly quickly. It didn't keep going forever with a constant velocity, same speed and same direction. Why was that? Why didn't we have a uniform motion that continued? Well, then maybe there was a net force on this that didn't allow that to happen. And that force, of course, is going to be, that force is friction, such that if I give a small velocity to my chair, very, very quickly, it comes to a stop because of the frictional force between the ground and the wheels. And so in this case, we don't have a situation where we have a net force of 0. And so it's really kind of incredible that Isaac Newton was able to come up with this relationship here on Earth when it's very difficult to find a situation where you do have a uniform motion and it doesn't quickly come to a stop. And he was, in fact, the first one in Western science to come up with the notion of that an object in motion wants to remain in motion. Before this time, it was thought that nature naturally brings things to rest, that rest was the natural state of objects in the universe, and that is not the case. So where can we go to demonstrate this? One place would be outer space. If we head into outer space and get far, far away from the gravitational pull of objects, we should be able to basically get in a situation where there is no net force, and we can test Isaac Newton's law. So let's give that a shot. Okay, and here we are in outer space, and we're far, far away from any gravitational pull or any other forces. And now if we try Newton's law, we should see that it in fact works. So again, if we have an object at rest like this chair, it's going to remain at rest. And if I was to throw anything in outer space, to give it some kind of initial velocity, it will continue to have that initial velocity unless it encounters some sort of force or hit something or whatever forever. And so in space, we can give objects an initial velocity and they will have that velocity forever and ever as long as it's got no gravitational pull slowing it down. And so here we go. Let's give it a shot and see if it works. The natural state that matter has is to keep moving if it's moving and to not move if it's not moving. But it's only forces that change that state, can go from rest to motion, from motion to rest. And that's essentially what Isaac Newton is getting at here. The second law states that if the resultant force acting on an object is non-zero, that is basically if you add up all the forces on an object and you get a number that's not zero. Now sometimes a force can have no forces on it, and so obviously it has a force of 0, but other times you can actually have 2 or more forces on an object, but they add up to 0, as we'll see. But this law is looking at what happens if your force is non-zero, the total force. Well, in those cases, the object experiences an acceleration. And that acceleration is the key link between forces and kinematics. It's the key driving force between how we define the motion and what causes the motion. What does force do? It creates an acceleration. Now that acceleration is not just dependent on the force, it's also dependent on the mass and the distance. And by distance we mean like if, for example, the sun was applying a force of gravitation onto the Earth, the mass of the Earth makes a difference, but so does how far away the Earth is. And what we basically have is that the acceleration is proportional, that's the proportional sign, to force, and it is also inversely proportional to mass. The more massive an object is, the less it's going to accelerate with the same force. So if I, for example, created a force on one object that is twice as massive as another object, the acceleration will be twice as small on the more massive object. This eventually leads to our first equation for forces, and the most important of them all, and that is that F equals ma, or force vector equals mass times acceleration vector, where this Fr is not a specific type of force, it is the resultant force, it is the net force, it is the total force. It is what happens when you add all the forces on an object up. So this is our resultant force. M is mass, and A is acceleration. And so the last of Newton's laws that we want to mention is Newton's third law, naturally, but it's going to prove a little bit more complicated, and we'll deal with the implications of Newton's third law later in our lessons on forces, but let's mention it now for completeness. The third law can be written very formally, but let's write it first sort of informally, because we all recognize this law. It's used both in science as well as, I think, in it's almost become a saying, if you will. Every force has an equal and opposite reaction force. Now, what does that mean? I mean, it basically means like if you apply a force onto an object, that object is applying a force back onto you. Anything that is applying a force onto something else is feeling an equal and opposite force. And what do we mean by opposite? What do we mean by opposite direction? Equal in magnitude, but opposite in direction. We can write this a little more formally in the following way. Another way of saying the same thing, a little more scientifically, is that if two objects interact, the force exerted by object 1 onto object 2, it doesn't matter if this is you pushing a shopping cart or the sun applying a force onto the earth, is equal in magnitude and opposite in direction. To the force exerted by 2 onto 1. And this is a crazy, crazy important law. It is responsible for so much of motion that we understand it. Like if I wanted to go in that direction, basically how I get there is to apply a force in this direction on something else. You see this very, very obviously if, let's say, I was some kind of a rocket. How does a rocket launch up into space? It's basically pushing backwards. It's using a propulsion backwards to go forward. What about if you're swimming? If I wanted to swim in that direction, I'm essentially pushing water backwards and the water is pushing me forward. Well, walking is actually the same thing. If we're walking, what we're basically doing is we're applying a force down and back, and the ground is pushing back at us with an equal and opposite force, allowing us to move in that direction. And like I said, this will be very, very important, but for our purposes, we're going to come back to the third law a little bit later. We're going to focus on the first two laws, especially law number 2, initially, until we get used to dealing with forces. And so just to end our little introduction on forces, we should mention how we measure forces, that is the units. And specifically, the SI units for force, well, if you look at the equation F equals ma, well, the units of mass in SI units are kilograms, of acceleration are meters per second squared, and so our units for force are kilograms, meters per second squared, which is a mouthful to say the least, and so we give it an equivalent unit of capital N, which is called newtons, after Isaac Newton. And so we'll just get rid of this. Write that as force SI units. And so just for a second, going back to this equation, F equals ma, and that is the resultant force is equal to the mass times acceleration. We called Fr this resultant force, but I think we need to explore that a little bit deeper to make sure we're all on the same page with what that resultant force is. Now, some people will call this the net force or the total force. It doesn't really matter. Feel free to label it or call it whichever you like, as long as you realize that it itself is not a force. It's not an example of a force. It is the result of all of the other forces that we're going to learn about. So the resultant force, or the net force, or perhaps you prefer the vector sum of forces, all are equivalent. And all of them are a result of all forces on an object. It itself is not a force. And so this equation F equals ma is not used for individual forces. It's only used for the net force, the resultant force, when we add up all of those other forces. So how do we add up those forces? Well, they're vectors, and so we have to add them up vectorially. The resultant force, or the net force, you might also see it as the sum of forces, written like this. So that is the sum sign right there, force, and perhaps we have an I number of them, so we can add them all up. And if we do that, it's essentially like adding up each individual force on our object. F1 plus F2 plus F3 all the way to our final force. Now keep in mind that each of these are vectors, and so they have to be added vectorially. We can't just add them up as numbers unless they were all going in the same direction, which they are most often not. And so we need to treat them as vectors, and that means components once again. Basically, you're not going to use the F equals ma equation by itself. You're going to use it in each of the individual directions that we have. So Newton's second law is only actually used in its component form. And so let's write it out. F equals ma in the x direction is just this. Oh, and that would be the acceleration only in the x direction as well. So what does that actually mean? It means if you add up all of the forces only in the x direction, they're going to be equal to the total mass multiplied by the acceleration of the object in the x direction only. Now, if I have a force that is neither in the x nor the y, then I have to take the component of it in the x direction, how much of it is in the x direction, and then use that same equation. Some of it perhaps is in the y direction, and we have an equation in the y as well, where the sum of forces in the y is going to again be equal to the total mass multiplied by the acceleration in the y direction. Now, as far as what direction our object is going to accelerate in, will it have an x component of acceleration and a y component of acceleration? We'll see very quickly that what we tend to do is set up our problems so that our x and y axes is in the direction of acceleration. So usually what happens is you get an acceleration in one direction and not the other direction. But we'll have plenty of time to see that as we go. All right, so now we're ready to try our very first example. Let's try the following. Let's pretend we have a situation where you are teaching your friend to skate. And we're doing this problem on ice, as a lot of these problems are done on ice or snow, to reduce friction to basically nothing. And so we don't want to take into account friction. Your friend, let's say, has a mass of 65 kilograms, is motionless on the ice. That's just a weird way of saying they're stopped. They're not skating. They're just like this because they're scared. They're scared. They're like, oh man, I've never skated before. What are you going to do to help your friend out? Well, why don't you apply a horizontal force on your friend? You push them. As I often do when I do first examples in a new field, I use very, very specific language to make sure that we all understand what is happening. And then over time, as we get used to the situation, I will use more common language. And so you'll apply this horizontal force on your friend for 2.0 seconds. So you basically walk up to them, behind them, you start pushing them for 2 seconds with a force of 88 newtons. What is your friend's speed now? At the end of that 2 seconds, what is your friend's speed? Okay, so what's going on here with a problem like this? What is your friend's speed? That sounds like kinematics. Is this a kinematics problem or is this a force problem? Well, let me see what I've gotten. I've got mass, that's definitely force. I've got a horizontal force of 88 newtons, that's force. I've got time, that's 2 seconds, that's kinematics. And I'm asked for speed, that's also kinematics. So there seems to be a mix of both kinematics and forces in this problem. What's the key link between kinematics and forces? That's right, it's acceleration. Acceleration appears in both of them. And so what we're going to need to do at some point is definitely to calculate the acceleration of your friend and then use that in our kinematics to solve this problem. Now there is only one force in this problem, and we know what direction it's going in. It's going in the horizontal, and so we're going to very quickly jump to F net in the x direction equals 88 newtons. We can see that very, very clearly. That's the direction of motion. That's the direction that we care about. And so we're not even going to do kind of an F net calculation. That often ends up being the hardest part of force problems. Instead, we're going to jump right to solving our acceleration and then using that for kinematics. So kinematic-wise, what do we have? We've got the time of 2 seconds. Well, we have the initial velocity, don't we? I'm remembering my kinematics now. Our friend is not moving. They're just standing there. And so let's set that to 0. And let's call this V initial x. And we're also going to have x initial as well. We'll start our problem at 0 if that's helpful. I'm not sure that it is. And finally, what are we looking for? Final velocity. That's what we're trying to figure out. And realize very quickly, even if you didn't realize this was a combination of forces and kinematics, is you just have to look at the kinematics problem. You're looking for this kinematic value of VFX, but you hardly know anything in the x direction. You hardly know any kinematic values at all. And so clearly we need some more information. And so for us to get V final x, I realize that I need to find the acceleration in the x direction first. I'm going to have to find what ax is and use that to solve the rest of my problem. Okay, so we have a force, we have a mass, we're trying to find acceleration. Clearly what we're going to use is our F equals ma. And so let's have that F net equals mass times acceleration, Newton's second law in general. We're applying it to a specific direction. In the x direction, this becomes like so, allowing us to solve for the acceleration as simply F over m. Throw those numbers in. We have 88 newtons divided by 65 kilograms, giving us an acceleration of 1.35. Let's keep an extra digit there just because the 5's a bit middle. So we've got 1.354 meters per second square. That's the acceleration of your friend. Now your friend is accelerating from rest for 2 seconds. And so to calculate the final velocity, I'm going to use equation 1 for my 3 original kinematic equations. Vfx is equal to v initial x plus a times t, just like that. And so let's throw in the values that we have. We already know that this was 0, and the rest of the problem is already ready to go. A is 1.354. I applied that acceleration for 2 seconds, or you did, I should say, giving me a final x of 2.7 meters per second. All right, super, super easy. Easy forces, easy kinematics. What was the point of that example? To show you the link, between the two. And what is the link between the two? Acceleration. When you calculate acceleration in kinematics, you can use it in forces. You calculate it in forces, as is more commonly done. You have the acceleration for the kinematic problem. Excellent. Okay, so that was a very quick example for one forces, but as soon as you get more than one force, it becomes much more complicated. All right, so now we're going to look at the techniques we use to solve the multi-force problems. And we're going to have to come up with sort of a step-by-step way of handling these more complicated problems. And so let's talk strategy through how to solve problems with multiple forces. All right, so whenever you have a problem that has more than one force, I want you to start by drawing a free body diagram. Now, you're used to drawing diagrams when it comes to kinematics, but free body diagrams are different. They are very, very specific in what gets included in these problems, and they are actually 4 marks. When you do a long problem that's a force problem, there are marks involved in you doing a proper free body diagram. Yes, everything you do after that is dependent on having your free body diagram correct, but they themselves show a great deal of understanding. And so it's always going to be important to draw a free body diagram. All right, so what is a free body diagram? Sometimes you'll see free body diagram just written as FBD. It basically is a diagram that shows all important objects and the forces on them. And it can have multiple parts to it. You can consider it multiple diagrams. Each object gets its own diagram. So a diagram, maybe we should write it like this, like potentially S. We'll get rid of this A. So diagram or diagrams of all important objects and the forces on them. Plus, your diagram has to include an axis, but that's no surprise to you. And so why don't we do a very, very quick example, and we'll keep this example going through all of the steps just to demonstrate a little more exactly what I mean. And so what if I had a problem with a chandelier? Let's say we have a ceiling. That indicates a ceiling right there. And we've got this real world chandelier hanging off of it. So I'm going to draw a chandelier here. It's going to be beautiful. It's got like this, like that, and this. Oh no, it's starting to look like a spider. Oh no. Beautiful. Okay. There we go. So this is our real world picture of a chandelier. And let's say that we had a problem concerning this chandelier, and we had to draw a free body diagram of the chandelier because it's an important part of our question. And so let's take this real world picture and draw the free body diagram of it. A free body diagram is basically anything that has mass is drawn as a circle or a square. And so we'll take our chandelier here, put M for mass on it. Perhaps the mass is given to us, perhaps not. And then we draw our forces on that object. And so if we're concerned just with the chandelier, the massive part right there, what forces are on our chandelier? Well, it's not going anywhere, so I reckon those forces are balanced, but what is actually on it? Well, if the chandelier is on the surface of the Earth, or near the surface of the Earth, then there is a gravitational pull downwards. So the force of gravity is definitely trying to pull this downwards. And we'll learn about the force of gravity in just a second. Conversely, there has to be something holding it up, something that is stopping it from falling towards the ground. And that something is the rope. There's a rope here, or maybe some fancy chain or something like that, that is holding this object up. And so the force associated with that hanging motion is called tension. There's a tension in that wire, and that tension is balancing gravity such that our mass is not going anywhere. It's not going up, it's not going down, because those forces are equal and opposite to one another. And finally, Let's slap on an axis to get our full free body diagram. Plus y plus x. And so there we go. We've got our free body diagram, and we are ready to go to the next step. But not quite, because as we've been doing this, we have talked about for the very first time two new forces, the force of gravity and the tension force. So let's introduce those formally as we go on. So let's start with the force of gravity. Force of gravity is a super important force here on the surface of the Earth. It exists all over the universe, but the force of gravity that we're going to talk about, Fg, that is capital F sub g, is the force of gravity due to the Earth near the Earth's surface. So this is going to be experienced by all objects. Near the surface of the Earth. So even if you're on the top of a mountain, that's close enough to the surface of the Earth. The depths of the ocean, same thing. Now if you're on the moon, clearly it's going to be something very different. So that is going to be a vector that always is going to be pointing downwards. The force of gravity is always trying to push objects, or pull objects if you prefer, towards the center of the Earth. Not just towards the ground really, but actually towards the center of the Earth. If you think of the Earth as the sphere that it is, everything is actually being pushed towards that center. But when we talk about an object on the surface of the Earth, we're zoomed in so much that we're basically just talking about down. That's which way an object is going to head. The force of gravity on everything is pushing us downward. And so we actually have a formula for the force of gravity. Unlike some other forces, this one has a very exact value. Mass times gravity, mg, where that g is an acceleration. It's the acceleration due to gravity that you're very familiar with already, and that is 9.80 meters per second squared. And so this is the magnitude of the force of gravity. And this is also known as weight. And so I've been very deliberate to use the word mass as opposed to weight, because weight has a different meaning than mass. Mass is an absolute term defining the quantity of matter, while weight is actually a force. It's dependent both on the mass as well as the gravitational force on our object. And that's where we get the words like weightless from, for example. And so our g, if you recall, please remember, is positive. It's the only time I ever write the positive. I just want to stress it's positive 9.80 meters per second squared, not negative. We are calculating the magnitude of the force. It's equal to mass times gravity, where gravity is positive, mass is positive, you get a positive force. But that's just the magnitude. The direction is downwards. Now, if you set your direction of your axis upwards positive, then clearly Fg is going to be equal to a negative value. But G itself is positive. Don't make that mistake, otherwise you'll end up doing two negatives. So that's it for the force of gravity, and we will use it in almost every problem that we do. Let's compare that to tension. So tension, given by the capital letter T, is has no formula. There's no specific value for the tension of a rope that is something is hanging off of, for example. It varies. It depends on everything that's happening in the problem. And what we want to think about is the direction of tension. The direction of tension is going to be more important to us since we don't have a formula. So tension is in the direction along the rope, string, or wire and so if we have a problem that has a rope on it, a string, a wire, doesn't matter, and it's pulling something or something's hanging off of it, well then the tension is along that wire, and specifically it is away from an object's mass. What that means is tension is always pointing along the rope away from the mass. Let's take a look to make sure we understand that phenomenon. So imagine that I have this wire right here, and I'm going to hang something off of it. Pretend I just have something hanging off it. So just think about this fist, not the one on top holding it. And so if this object is hanging off of this, there's a tension in the string. You can see the tension in the string. This is no tension. This is tension. So how much, or I should say, what direction is that tension in? Well, think about which way this object is being pulled. Think about which way this object wants to go due to the tension alone. Well, if there was no force of gravity pulling it down, it would in fact be going upwards. Same thing if you just have two wires like this. Think about it. What direction is on each fist due to the wire? Well, each one is pulling the mass along the rope away from it. So the tension in this rope, well, if you're doing the free body diagram of this fist over here, it would be going that way. If you did the free body diagram of this fist over there, is being pulled in that direction. And so tension is in the direction along the rope, string, or wire, away from an object's mass. And please keep in mind there is no formula for tension. Now that doesn't mean we can't find tension. We can certainly find tension when we are doing our Newton's second law problems, but there's no direct formula for it. So no formula for tension. Okay, so the second step, finally, once we have our free body diagram, what you do is you write out Newton's second law. Strange. Write out Newton's second law. And you actually have to do it for each direction for each object. So write out Newton's second law, not just once, but sometimes many times. Has to be done for each relevant direction for each relevant object. All right, so write out Newton's second law for each relevant direction for each relevant object. And of course you're saying to yourself, how do you know if something is relevant? How do you know if a direction is relevant? Well, essentially, if you have any forces going in a direction, it's relevant. If we have this problem that we had before, well, only the y direction is relevant. Only the y direction has forces going up and down. There is no forces in this direction. So this problem has one relevant object, basically as many objects as you drew a free body diagram for, and one relevant direction. So we're only going to write Newton's second law once. But if we have one with multiple masses and forces in multiple directions, you can get 4 equations, 4 Newton's second laws, etc. And so here we go. Let's write out what we're talking about. So I want you to write F equals ma in general, showing that you know you're applying this rule, and then break it up into its components. Write down that the sum of the forces in the y direction is equal to mass times acceleration in the y, and that the sum of the forces in the x direction is equal to mass times the acceleration in the x direction. Now, once again, please remember, what is this value here? This sum of Fy. This is the sum of forces in that direction from our free body diagram. And so all we're basically doing is saying that, look, the sum of the forces in the y direction, that's not a force itself, it's all the other forces put in there. And so we have to add them up. And sometimes you're subtracting them, of course. It depends on which way you've set your positive direction. And so let's see a very quick example of that. We'll continue our example of our problem up here. And so now I have my free body diagram that I wrote. I see that I only have one important direction, and so let's go ahead and write our F equals ma for that. So let's write example continued. That's from above. And so again, same thing, sum of the forces is equal to mass times acceleration. I know I only care about this in the y direction. And so I write those forces down. I write them down here. The sum of the forces in the y. Well, let's go back to my diagram really quickly. Let's keep it above my head here. And so what we're seeing is tension up in the positive direction and force of gravity down in the negative direction. And so that sum is T plus negative Fg. Of course, you can write T minus Fg. All I'm showing you is that it is in fact a sum. I'm adding T and then I'm adding negative Fg. And I don't have to worry about the vector sign or anything like that because these vectors are in my y direction. And so all I've done is expanded this. This is what that is. That's where that came from. And now I take this value and I put it here. And so that's still mass times acceleration, but specifically the acceleration in the y direction. And so we can just write it once without the sum sign. I actually don't need that sum sign. Once you've written down all your values, your equation is just T minus Fg equals mass times acceleration in the y direction. We won't go any further at this time because we want to save the next step for number 3. Number 3, once you've done your free body diagram, once you've done your F equals ma, now you could do this before, but at some point you need to make yourself a list of known quantities. And identify what you are looking for. All right, so we made a list of our known quantities. We've identified what we're looking for. And again, if we continue our example, it would look something like this. Let's pretend in our problem we had the mass of our chandelier. Let's say it was a big, heavy, fancy 25 kilogram chandelier. That seems dangerous. Do we know anything else about our problem? Well, one thing that naturally flows from it is you do know the acceleration of the chandelier. The chandelier is neither going up nor is it coming down, and therefore it has an acceleration of 0. It's completely balanced, if you will. And so what we're actually going to be asked to find in this problem is the tension. How much tension is in that rope? So we've made our list, feeling good. Let's move on to number 4. Now we start to get into the actual mathematics. Solve for the unknowns. And in problems where you have 3 or 4 F equals ma equations and you have 3 or 4 unknowns, That can be quite challenging. In our own problem, it's super, super easy. We take our T minus Fg equals ma equation, and we sub in what we know. So starting with T minus Fg equals mass times acceleration in the y. Well, we said the acceleration in the y is 0 because our object is neither going up or down. And that leaves us with tension equals Fg. But I have an equation for Fg. In fact, I probably should have put it in by now. Why don't I do that? Let's move this. Well, no, we could do it at this stage. We'll do it in 2 steps, so it's very clear. So that equals T equals Fg. Fg, force of gravity, that's F sub g, is equal to mass times gravity. Please don't get this g mixed up with that g. Yes, they're the same g's, but it's not F times g, it's F sub g, the gravitational force. While this other mg is mass times gravity. 2 separate values multiplied together. And what is that going to give us? 25 times 9.8. We'll stick with 9.8 for our little g, giving us a total tension of about 245 newtons. If you round that, you should probably round that to 250, right? Since we have 2 sig figs. Okay, that's good. All right, excellent. And so those are the steps that I want you to employ for every force problem you do that has multiple forces in it. And so let's jump into an example next where we actually get to employ all of these steps. Okay, and so now let's try our very first difficult example of forces. In this problem, we have ourselves a piñata of mass 3.0 kilograms hanging from 3 wires in equilibrium. And the question is asking us to find the tension in all of the wires. Now, what do we mean by equilibrium, first of all? Equilibrium means that everything is balanced. Forces are balanced, resulting in no acceleration, in fact, no motion at all in this case. And so we have our piñata. In case you don't know what a piñata is, it's like a children's birthday party object filled with candy and other things like that. And the kid hits it and the candy falls out. It's fantastic. Anyway, in this case, what we're trying to do is figure out what the tension is in all 3 wires. And the way we're going to do that is to do our standard sort of setup for a multi-force problem like we've talked about before. And so a couple of things that I need to add here are the angles of my wire 1. Theta 1 is 60 degrees. And my angle 2, theta 2, is 25 degrees. What that represents is this angle here and here. And so these 3 wires are holding up this piñata, and there's tension in them, right? You've got a wire, 2 wires going like this, another wire going like this, an object hanging off of it, and it's pulling on all of those wires. Each one has a tension in it, and we can calculate what the tension is in each of those wires using the techniques we've talked about in our previous lesson. And so, if you recall, our very first step is to draw a free body diagram. And so we have to draw a free body diagram of all the important objects in this problem. And I look at them like there's only one object in this problem. It's the piñata itself. This is really the only thing that has a mass, and I think that mass is given, yet 3 kilograms. And so you figure we could just draw a free body diagram of that. But we can't. There's a problem with that. The problem is we're trying to find the tensions of wires 1 and 2 in this problem as well. And wires 1 and 2 don't actually touch the piñata. And so if you draw the free body diagram of just the piñata, you're going to leave out tension 1 and tension 2, which are values that we have to find. And so, in fact, we're going to need 2 free body diagrams in this problem. And yes, we'll draw a free body diagram of our piñata, but we're also going to draw a free body diagram of that knot there, that node where the wires 1, wires 2, and wires 3 connect with each other. It's massless, but there is forces acting on that location. And so we're going to draw a free body diagram for that as well. Let's get started. All right, let's draw the easy one first. So we've got a mass. I'm going to draw a square this time. It's going to represent my piñata. And I look at the forces on the piñata. Well, it's near the surface of the earth. I imagine it's not a space piñata. And so I'm going to draw the free body diagram of the with the force of gravity downwards. And so I know what that force of gravity represents. It's the force of the earth pulling the piñata down. But the piñata is not going down. It is balanced. It's in equilibrium. And so there has to be a force up. And so it has to be a force related to this wire 3 that's attached to it. And we're going to call that wire, or the force due to that wire, I should say, tension 3. And it is upwards. I know it's upwards because I know that tension always works along the wire away from the mass. That's how it's holding this object up. That should be a nice straight line. Let me see if I can straighten it a bit. Yep, that looks great. Okay, and so good free body diagram for our piñata? No, it's missing something, of course. It needs a axes. And the axes could have the X and the Y placed on it, but really all I need is one of those two. And so let's call this direction plus Y. Things are happening in the Y direction. Nothing's happening in the X, so I'm not even going to label that. It's not an important direction for me. Moving on to our next free body diagram, let's draw the free body diagram of our node. And so we draw that little dot right there. It has no mass, but it does have forces coming off of it. The various forces are pulling it in all directions. It is also not moving. It's got 2 wires going that way and 1 wire going that way, and they're all pulling away from the point, but nothing is moving. They're all balanced with each other in equilibrium. And so this time our tension 3 is actually going downwards. It is the same tension as that tension, but in the opposite directions. We're seeing the equal and opposite force of the tension on the piñata on this node. What else do we have? We've got our T2. T2 is along this way, and it is pointing in that direction, T2. And finally, T1. Same sort of thing, along the wire, away from the point that we're looking at. And so we've got ourselves our 3 tensions. Let's realize that we need an X and a Y direction that has those 2 directions in it because everything is not happening in one dimension. T1 and T2 have components both in the X and the Y, so we have to take that into account. And so that looks like a good setup, except for one little tiny thing. That little tiny thing that I don't like about this setup is that I have 2 Y directions. Now, I realize they're going in the same direction, and you're like, well, they're just the same things. What's the problem? The problem is I'm actually going to eventually do an F equals ma equation for each important direction. And so I want to label those directions as distinct directions. This is going to be especially important when we end up with multiple masses. And maybe at some point you're going to want to make Y up for one and Y down for the other. There are circumstances like that that are coming fairly soon. So I want to differentiate between my 2 Y directions. I'm going to call that Y primed. So now I go into my next step after drawing these lovely free body diagrams, and I apply my F equals ma equation. F equals mass times acceleration. That's it in general, but what I want to do is apply it to all the important directions. Well, how many important directions do I have? 1, 2, 3. I need 3 F equals ma equations. Let's write them down. Again, we'll start with what I consider the easiest one, which is that the sum of the forces in the Y primed direction, that's the easiest direction, prime, is equal to what? Well, this step, all you're doing is reading it right off your free body diagram. You've got T3 going up, you've got FG going down. We said that plus y primed was positive upwards, and so all we have to do to put that together is say that T3 minus mg is equal to this part, or specifically mass times acceleration in the y prime direction. That's me applying my F equals ma equation to the mass, the piñata. Those m's are the mass of the piñata. G is, as we know, T3 is an unknown. But we do know one other thing. We know what AY primed is at this time. You can actually get rid of it. Because everything's in equilibrium, I know there's no acceleration. The mass is not accelerating. This is 0. And so we can write really quickly, since it is in equilibrium. Now keep in mind, if it was moving at a constant velocity, it would still also have an acceleration of 0. But if it's not moving at all, then I am certain it is 0. And so now for a much harder F equals ma, let's try to figure out what it is for the x and the y direction of our second free body diagram. And I think I'm actually going to cut and paste this and draw some more stuff on it below. I don't want to mess up my original free body diagram. It's great the way it is, but I feel like I'm going to need to think about things a little bit. And so I've got another one down here that I can play with. All right. So what is my sum of forces? Let's start with the x direction. Well, in the x direction, I have two forces. T1 and T2 both have components in the x direction. Let's draw them out just for fun. Okay, T2x looks like that. And T1x looks like that. So here we go, T2x, T1x. And of course, that's in combination with this one, which is going to be T1y, and this will be T2y. We'll deal with those ones later, but for now, we have everything in its x and its y component, and if we're looking for the sum of the forces in the x direction only, then I can see that T2x is going in the positive direction, and T1x is going in the negative direction. And so we go ahead and we write that the sum of the forces is T2x minus T1x. And again, there's no acceleration. In fact, at this time, there's not even any mass. And so that is also equal to 0. Those two forces are equal to each other, and that's why it's not moving left and right. And similarly, we can do the same thing in the y direction. This one just a teeny bit more complicated. In fact, I recommend you give it a pause right now and try to write down the forces in the y direction. Go ahead and try that right now. Okay, we're back, and what we see, of course, is the two tensions going up, T1y and T2y are both up, and they are balanced by T3, which is downwards. And so this time, the sum of the forces is equal to the following: T1y up plus T2y up, and minus T3 down, and that is again equal to 0. All right, great stuff. And so what we've done is we've constructed 3 equations, 1, 2, and 3. And now it's time to focus on what we're actually looking for. What do we have and what are we looking for? Let's make a very quick list. We have the m, the mass, 3. We have a, acceleration. Oh, sorry, not a. Ugh, my bad. There's no a. it's g, which is 9.80 meters per second squared. And then we have our angles as well, which haven't come into play yet. But what are we actually looking for? We want T1. We want T2. We want T3. And so these are many unknowns. And for us to get to them, we're going to have to realize that we need to rewrite our equations. Our equations have the unknowns T3, but they're in the terms of T1x and T2x and T1y and T2y. That's too many unknowns. That's 5 unknowns right there. Let's get it down to 3 by taking our T2x, T1x, T1y, T2y, and replacing them with the T1 and T2 so that we have fewer unknowns. Okay, so let's rewrite these 3 equations. I'm going to start with equation 1. And to be honest, when you rewrite them, you start to do math with them. You actually don't need this part of it. I'm not saying scratch it out. I'm saying when you rewrite it, you don't have to rewrite the sum of the forces in the various directions. All we're really writing down is equation 1, T3 equals mg. Now, looks like I actually skipped a step, which I'm not happy about. Sorry about that. You and I both know that the force of gravity is equal to mass times gravity, but it is actually incorrect for me to write it right into the equation. This one should have definitely been Fg. Just in my head, I skipped one step ahead. That's the force of gravity, nothing else. But now, when I move this to the other side, then I can sub in mass times gravity, and we're good. So our second equation becomes T3 equals mg. For those that don't quite see it, we can write it a little bit differently. Let's write this as T3 equals Fg, which is equal to mass times gravity. That's great. And so now let's figure out how we can simplify our second equation, that is the sum of the forces in the x direction. Well, what is T2x? Well, if I recall, looking at my original picture here, I'm given these angles. That is, this angle here is theta 2. And that also means that this angle here is also theta 2. You can do that with what's called the Z rule or the Zorro rule. So for example, if I have 2 parallel lines like this angle here has to be equal to that angle there. And so the same thing must be true for the other side as well, where that leads this angle here to be theta 1. Okay, what that means for us is that T2x is just going to be equal to the hypotenuse, T2, multiplied by the cosine of theta 2, since it's the adjacent side to the angle. Again, trigonometry you should be used to by now. And so our second equation, instead of writing T2x, I write T2 cosine of theta 2. Looking at my next term, T1x. T1x is this value right here. To get that, all I'm doing is taking the hypotenuse, T1, and multiplying it by the cosine of theta 1 to give me the x component. And so what was the original equation was T2x minus T1x, and so that becomes minus T1 cosine of theta 1. All of that is equal to 0. Finally, I get to my third equation, and this time it's in terms of y. I know these are going to be the sine components. Obviously, they're opposite to the angle, and so T2y is just T2 sine of theta 2, and T1y is T1 sine of theta 1. And so let's write that down. So that was T1y. Here's our T2y. And T3 remains as it was. All right. So I've rewritten my 3 equations. They look really nice. And I can even emphasize that I have 3 equations and 3 unknowns. I can do this. 3 equations and 3 unknowns is totally solvable. In fact, it looks like T3 can be solved right away, and so feel free to do that if you like. You essentially have 1 equation here, and then 2 more over here and over here, giving us our T1 and our T2. So let's see, what would be a good technique? Well, we have T3 in terms of mg. This is what I like to do when I have 3 equations and 3 unknowns. It happens quite a lot in first year physics. What I do is I look for the equation that has all of the terms in it, as it often does. That one tends to be the most long one, complicated looking one, and that's equation 3 in this case. It has T1, T2, and T3. And so what I want to do is I want to substitute into that equation so that I just have the one unknown. So if I substitute T3 into here, and then let's solve for T2, I can put that into there, and then T1 will be the only unknown left in that third equation. Let's go ahead and give that a shot. So I'll start with equation 2. And I'm going to solve for T2. And so T2 cos of theta 2 is equal to T1 cos of theta 1. I'm solving just for T2. It's equal to T1 cos theta 1 divided by cos theta 2. So far, so good. Now I want to take that value and I'm going to sub it into 3 here. And I already know what T3 is. It's just equal to mass times gravity. And so now that I have T2 and I already had T3 from equation 1, I can sub them both into the third equation. So sub 1 and 2 into 3. That looks easy enough. Let's give it a shot. So now equation 3 looks like the following. We still have T1 sine of theta 1, but now our T2 sine theta 2 is going to look very different. We're going to use this term here for T2, leaving us T1 cos theta 1 divided by cos theta 2, all multiplied by sine theta 2. And then finally, we have our T3, which was just equal to mass times gravity. And so this becomes mg, and all of that is equal to 0. And now there's a complicated looking equation, certainly, but we just have one T1, only a single T1, which is going to make things pretty straightforward. And so let's clean this equation up and solve for T1. Well, you move mg to the other side right away, but also notice this term right here. Sine theta 2 divided by cos theta 2. You can simplify that. You don't have to, but I like to make things simpler. Sine divided by cosine of the same angle is just equal to, there's a trig identity, tan theta 2. And so let's write it in the following way. We'll write T1 sine theta 1 plus T1 cosine theta 1 tan theta 2 is equal to mg. We'll factor out our T1, leaving us sine theta 1 plus cosine theta 1 tan theta 2 is equal to still mg. And finally, we can solve for T1 by dividing all that stuff by both sides. And you get T1 equals mass times gravity divided by sine theta 1 plus cosine theta 1 tan theta 2. All right, that looks good to me. So plug the numbers in and see what you get. Feel free to pause it at this point to check your work. I get 3 times 9.8 all divided by, now make sure your calculator is in degrees, sine of 60 plus the cosine of 60 times the tan of 25. Now remember that we're solving for T1 specifically here. This is the tension in our first rope. And if you plug that into your calculator, what do you get? I think I hear somebody saying 26.7 newtons. That is correct. And now that you have one of the unknowns, it's super easy to find the other two because we already have an equation waiting for us right here. T2 was already put in terms of T1, and so now that we have T1, super easy. And T3 was always easy. We could have solved it at any time. So finishing this problem off, we take our equation 2, and we have that T2 is equal to, as we said, T1 cosine theta 1 divided by cosine theta 2, or 26.7 multiplied by the cosine of 60 divided by the cosine of 25. Throw that into your calculator to get a value for T2 of 14.8 newtons. And then finally, to finish the problem off, we're going to get our T3, which is of course just equal to the gravitational force, or mg, 3 times 9.8, which should give us the biggest number of the three. That wire should hold the most tension, since essentially it's holding the piñata up, and then the other two are sharing the load on the piñata. And throwing that in our calculator gives us 29.4 newtons. And so I logically try to assess this. T3 is the largest, the other two are smaller. And I look at even the angles. Should T1 be bigger or should T2 be bigger? Which one is holding the more of the load, T1 or T2? Logic dictates, based on the angle, that T1 does hold more of the load, and that's what we figured out as well. With our T1 being equal to 26.7 newtons, T2 was 14.8 newtons. And finally, T3 is biggest of all at 29.4 newtons. And remember that these are forces, these are vectors, they have directions, and it is sufficient in these sorts of problems to write as directions as shown in the diagram. No one asked us to find any directions. They in fact were given, and so we can just write directions as shown in our free body diagram.